Hello everyone, this is Harrison Galway, and today I will be teaching you how to graph rational functions. Rational functions are functions in which there is some expression in the numerator divided by some expression in the denominator. So, in order to graph rational functions, there's this list of steps, and you can see it's somewhat extensive. But each step on its own is manageable, and if you go through these, it goes pretty smoothly. So first, I'll walk you through these steps, and also just in case you want to have this document with these guidelines, I'll make it available. But anyway, so the steps are: first, you're gonna factor everything as much as you can. The numerator and denominator, you'll factor them entirely. Step 2 is this isn't really essential for graphing, but it is good practice and can be useful. You'll state the domain, and the domain of a rational function will generally just be all x values except the ones that make the denominator 0. So we'll just exclude any values that make the denominator 0 from the domain. Step 3, we're going to look for holes, and the way you find holes, if there are any, is you look to see whether any factors cancel from the numerator and denominator. If they do, there's a hole. And in order to find out where that hole is, you're going to take the factor that canceled and set it equal to 0 and solve for x. That'll be the x-coordinate of the hole. Then, to find the y-coordinate of the hole, you'll just take that x-coordinate and plug it into the reduced function. The reduced function is just the function you get after you cancel those factors. So you'll take the x value of the hole, plug it into the reduced function, and that'll pop out the y-coordinate of the hole. So once you've done that, all the rest of the steps, you're going to use the reduced function. You can ignore the original one and use the function that you get after you cancel those factors, if there are any. So step 4, you're going to find the vertical asymptotes. And to do so, you'll just take the denominator and set it equal to 0. And you want to make sure to take note of the multiplicities you get when you find those vertical asymptotes. In other words, how many times you get each solution, because that'll have important implications when it comes to graphing when you get there. Next up is the horizontal or alternatively oblique, aka slant asymptote. And for that, there's this set of rules. Generally, what you do is you compare the degrees of the numerator and the denominator. And depending on which one has a larger degree, there will be a particular outcome in terms of this asymptote. If the denominator has a larger degree than the numerator, the horizontal asymptote will just be y equals 0. If the denominator and numerator have the same degree, you'll have a horizontal asymptote that will be equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. If the numerator is 1 degree higher than the denominator, or if the denominator is 1 degree lower than the numerator, you'll have a slant asymptote. And you'll find that slant asymptote by just dividing the numerator by the denominator. And you'll ignore the remainder when you do that division. That'll be your slant asymptote. Finally, if the denominator is more than 1 degree smaller than the numerator, you won't have any horizontal or slant asymptotes. So those are the rules. We'll practice using them, in the examples that we do, but there they are. The next thing you want to do, and this isn't always stressed, but I think it's good practice and can be very useful when graphing, is if you do have a horizontal or slant asymptote, you want to set your function, the reduced function, equal to that asymptote, because that way you'll find out whether your graph intersects the horizontal or slant asymptote. It's a common misconception that the graph can't cross horizontal asymptotes. That's not the case. Vertical asymptotes can never be crossed, but horizontal asymptotes are only significant on the very far right end of the graph and the left end of the graph. In the middle, they're unimportant. So you can find out whether your graph crosses through an asymptote by setting it equal to the function. So that's step 6. Step 7, find the y-intercept. And just like every other graph, you find the y-intercept by setting x equal to 0. Number 8, find the x-intercepts by setting the numerator equal to 0. So you'll take the numerator of the rational function and set it equal to 0. And just like with the vertical asymptotes, keep track of the multiplicities of those x-intercepts. Again, that'll be useful when you're graphing. Finally, number 9 is to graph. You're going to graph the function using the things you found, all those asymptotes and intercepts. And if there's ever any ambiguity, you can always just plot some points, right? Pick some x values and just plug them into the function and pop out the y values, and that can give you some guidance. But oftentimes you don't end up needing to. So anyways, let's move on and do a couple of examples. We have 3 problems here. I tried to have them include various aspects. So let's look at the first one. So we have a rational function here, and step 1 always is to just completely factor it out. Now, the top of this first rational function is linear, and there's no greatest common factor, so we're just going to leave that alone. But the bottom, there are a couple of things we can do. Firstly, there's a GCF of x. So we'll pull out an x. What do we have left? X squared plus 6x plus 9. And then, as always, when you're factoring, you have to make sure that you factored completely. And there's another factoring step we can do. This is a quadratic trinomial. And so what multiplies to 9 and adds to 6? Well, that's 3 and 3. So it has the same 2 factors. It turned out to be a perfect square. So all factored out, it will read x minus 3 over x times, and our factors were x plus 3 and x plus 3. We'll just do x plus 3 squared. All right, so all factored. The next thing that we do is we take a moment to state the domain. Now, for the domain, it really doesn't require a great deal of thought, because all you need to do is exclude any values that make the denominator 0. And we can make a number line to keep track of those. What values of x, when you plug them into this denominator, would make it come out to 0? Well, if you plug in 0, that's of course going to make the denominator 0. So 0 we're going to need to exclude. And also you can see if we plug in negative 3, that's going to make the denominator equal to 0. So we also need to exclude negative 3. But besides that, all x values are just fine. So everything else is going to be shaded. And you can see that our domain will have 3 intervals: negative infinity to negative 3, union, negative 3 to 0, union, 0 to infinity. And just a little side note, I'm a big advocate of making a number line because it makes it really easy then to use interval notation to state some set. So anyways, let's move on. So we've stated the domain. The next thing we do is we look for any holes. And the function will have a hole if anything cancels. But, we look at the numerator, where we have this x minus 3 factor, and the denominator, and there are no factors in common. Nothing cancels. So there are no holes in this function. Let's just write that down. No holes, because nothing cancels. Next step is to find vertical asymptotes. And to do that, we're just going to set the denominator of the function equal to 0. So we'll do x times x plus 3 squared equals 0. We'll use the zero product property. We get 2 solutions. We get x equals 0. And then we get, if we set x plus 3 equal to 0, we get x equals negative 3. But remember, really useful to keep track of multiplicities. X equals 0 we only got once, but x equals negative 3 we got twice. You can see that that factor is squared, so that has a multiplicity of 2. So those are our vertical asymptotes. We'll graph them. We'll graph everything at the same time. We'll leave that there for now. Next step is horizontal asymptotes. And if you recall, or slant, horizontal or slant asymptotes, to find those, we compare the degrees of the numerator and denominator. And to do this, you can look at the, this factored version that we have, or you can look at the original, really same thing, right? Because the numerator here is degree 1, and the denominator is, let's see, 1, 2, 3, right? Because this guy is squared. So degree 1 in the numerator and degree 3 in the denominator. And you could have seen that even more easily using the original, degree 1, degree 3, right? And if the denominator is a higher degree than the numerator, our horizontal asymptote is simply y equals 0. And make sure that you really write y equals 0, not just 0. I see students often writing just 0, but the horizontal asymptote's a line, so it needs the equation of a line. So you'll need to write y equals whatever it is. So fine, that's our horizontal asymptote, y equals 0, because the denominator is higher degree than the numerator. Next step is the y-intercept, and that's an easy step. To find the y-intercept, set x to 0, per the usual, right? So we can do that over here, y int. And to evaluate the y-intercept, we just set x to 0. So let's show our work. F of 0 equals, and then we'll use the factored version over here. We have 0 minus 3 over 0 times 0 plus 3 squared. Oh, but look, we get negative 3 over 0, which is undefined, right? Undefined. So that means that there are no y-intercepts. No y-ints. Which actually makes a lot of sense, because you'll recall that we had a vertical asymptote that had the equation x equals 0. So if there's a vertical asymptote here, we can't possibly have a y-intercept, so no surprise we didn't get one. Next is finding the x-intercepts. And unlike the y-intercept, we can't have multiple x-intercepts. You can never have multiple y-intercepts, because if you did, you would fail the vertical line test and it wouldn't be a function. But you can have multiple x-intercepts, and the way you find them is you set the numerator equal to 0. So we'll take our simple linear numerator, x minus 3, which we get from over here, and we set it equal to 0. And our solution is x equals 3, so that is our x-intercept. And just like the vertical asymptotes, always keep a close eye on the multiplicities of x-intercepts. So that's multiplicity 1, we just got it one time. So that just about does it for preemptory information. There is one step that I skipped, but it turned out not to be necessary. If you remember here, looking at the original steps, I mentioned we should always set the function equal to the horizontal or oblique asymptote. Oblique is the same as slant. We should set the function equal to the horizontal or slant asymptote to find points where they intersect. But notice our horizontal asymptote is y equals 0. So if our function intersects that line, that's just going to be an x-intercept, right? So by finding the x-intercepts, we really effectively already did that. So there is an exception. If your horizontal asymptote is y equals 0, you don't need to set the function equal to that. That's just the same thing as finding your x-intercepts. So let's plot everything we have. We have a vertical asymptote at x equals 0. Let's plot that. Okay. One down. We have a vertical asymptote at x equals negative 3. Close enough. We have a horizontal asymptote at y equals 0. So that's it for our asymptotes. Then we have, let's see, no holes, no y-intercept, but there is an x-intercept at x equals 3. So let's plot that x-intercept at x equals 3. That'll be right here. All right, and so then it's time to graph. Now, looking at this, it's pretty tough to know what to expect. Let's say we started here at this x-intercept, the only point that we have, and let's say we wanted to head left and try to predict what the function did as we went that direction. Should we go up? Should we go down? Should we go down and then up? How do we know what to do? And this is one of those circumstances where really the only way to know is to plug in a point. So what x value could we plug in? Well, either 1 or 2 would work, right? If we plug in either of those, we'll know the behavior of the function in that region. So let's just plug in 1. Let's evaluate the function at 1. So we'll do this over here on the side. We'll say f of 1, just to get some information, is 1 minus 3 over, we'll use the factored version, 1 times 1 plus 3 squared. So we get, let's see, negative 2 over 16, or negative 1/8. So we just found a point at 1 comma negative 1/8. So let's plot that. 1 negative 1/8. That will be right here. And that is some really useful information, because that tells me that if we start at the x-intercept, we need to head downwards in order to go through that point, right? So it answers the question of which way do we go. Now, once we pass through that point, what does our function do? Does it head down here and hug the vertical asymptote going downwards, or flip back up around and head towards the vertical asymptote skyrocketing upwards? And the way you can be confident about that decision is if you were to turn around and come back up, notice you'd be forming a new x-intercept, right? But you already found out that the only x-intercept is at x equals 3, this one. So you couldn't possibly turn back around, or you'd be creating things that you must not have. So our only choice is to head downwards here and approach that vertical asymptote. So we're going to use that logic really frequently. Like, how do we know which way to go? Well, we can't make any new x-intercepts, and that'll often be our guiding principle. Let's fill out the graph over here on the right. So this x-intercept, if you remember, it had a multiplicity of 1. And just like when you're graphing polynomial functions, when an x-intercept has an odd multiplicity, like 1, 3, 5, 7, 9, the graph goes through that x-intercept. So rather than bouncing off, we're going to go through the x-intercept. Now, on the very right end of the function, we ultimately have to realign, and approach the horizontal asymptote. So our graph will head back down and approach the horizontal asymptote, and that will be that. Now focusing on the middle region of the graph here, what we should do is, let's take a look. This vertical asymptote here was x equals 0. And we got it here, and it had a multiplicity of 1. Now, if your vertical asymptote has an odd multiplicity, like 1, 3, 5, the graph will have the opposite behavior on either side of it. So looking at this vertical asymptote, to its right, the graph plummeted downwards. But because it had an odd multiplicity, I know the graph must have opposite behavior on either side. So if on the right of the asymptote it goes down, on the left of the asymptote it'll have to go up. So that's how I know what to do on the other side. All right, now from here, let's see, I have choices. I could head down here to approach this vertical asymptote, or make a 180 and come back up here. But if I went down, again, I'd be creating a new x-intercept, which is not an option. The only x-intercept is x equals 3. So I'm going to turn around and head back up. Okay. Now we can use our vertical asymptote logic again. This vertical asymptote is x equals negative 3, which we find here. But that one had a multiplicity of 2. And, as you can probably predict, if the multiplicity of the vertical asymptote is even, the graph will have the same behavior on either sides. Since this asymptote has an even multiplicity, we went up on the right, we're also going to go up on the left. So the graph will have the same behavior on both sides, and that's what I do here. All right, so now I head over to the left. I ultimately have to approach this horizontal asymptote. Should I go through it? I can't. If I did, I would make a new x-intercept. So I'll just flatten out, and that's that. There's my rational function all graphed. So that's the first example. We saw a lot. We didn't see any holes that time, but maybe the second one will have some. Let's take a look. So step 1, per the usual, is to factor everything. So what we'll do is let's see, we can do a GCF on the top, right? And actually, let's save ourselves a little bit of work here so we don't have to write everything down so many times. We'll just take these expressions, the numerator and the denominator, and we'll just factor them over on the side so we don't have to keep writing so many things. So first we can pull out a GCF of 2. So we get 2. Oh, sorry, no, the GCF is 2x. I can do better. So 2x times x squared minus 9. And I can factor that even further because this is a difference of squares. So I ultimately get 2x times x plus 3, x minus 3. So that's the numerator. The denominator, which was x cubed plus 3x squared minus x minus 3. It's a cubic, which is a little bit scary. Factoring cubics can be harder, but whenever you have 4 terms, it's often a good idea to see if grouping will work for you. And in order to factor by grouping, you group up the first 2 terms, group up the second 2 terms. It may or may not work, but it's worth a try. And what we do is we pull out the GCF of the first 2 terms, which is x squared. What do we have left? X plus 3. And then we pull out the GCF of the second 2 terms, that's negative 1. What do we have left? X plus 3. And lo and behold, the things in parentheses here are the same, which is the signal that the grouping method did indeed work. And our factors that we get are the stuff that appeared twice, x plus 3, and the stuff on the outside, that's x squared minus 1. Can I go any further? Absolutely, because this is another difference of squares. So we'll factor that into x plus 1 times x minus 1, and voila. So after all that, we've gotten it completely factored. The top here became, let's see, it was 2x times x plus 3 times x minus 3. And on the bottom, we had x plus 3 times x plus 1 times x minus 1. All right, so it's all factored. Next step, we need to state the domain. So we'll write out the domain. And, the domain, all we need to do is exclude any values that make the denominator 0. So let's see, what would make the denominator 0? Well, it's really easy once it's factored to see what they are, right? Negative 3 would make it 0, negative 1 would make it 0, and 1 would make it 0. So let's just plot those real briefly. Negative 3, negative 1, 1. All of those are bad, right? All of those make the denominator 0 and they make the function undefined, but everything else is good. So our domain is now really easy to see. It's simply negative infinity to negative 3, union, negative 3 to negative 1, union, negative 1 to 1, union, 1 to infinity. So there's our domain. All right. Next up is we look for holes. And to find holes, we look for any factors that cancel. And this time we have one. The x plus 3 cancels from the numerator and the denominator. Now, the way that we find out where this hole is, it's a 2-step process, right? So, hole. First of all, to find the x-coordinate of the hole, we take that factor that canceled, x plus 3, and we set it equal to 0. We solve, and that's the x-coordinate of the hole. So the hole is at negative 3 comma something, right? To find the y-coordinate, we're going to use the reduced function. In other words, we're going to use the function that we get after canceling those factors. And I'm going to call it r of x, because technically it's not the same as the original function when we cancel those factors. It's very similar, but differs in its behavior at x equals negative 3. So we will write r of x equals 2x times x minus 3 over x plus 1, x minus 1, having canceled that factor. And to find the y-coordinate of the hole, all we need to do is take the x-coordinate of the hole and plug it into the reduced function. So we just need to evaluate r of negative 3. Let's do that work here. r of -3 equals, and so it's 2 times -3 times -3 minus 3 over -3 plus 1 times -3 minus 1. Okay, let's do a bit of math. So we now have, what's this? We have -6 times -6 over -2 times -4. So that's 36 over 8, which is, let's see, we can divide those both by 4, so we get 9/2. So that's the y-coordinate of the hole. The hole is at -3, 9/2. Good. All right, so we found the hole. Now the good news when you get a hole is that after you find it, you can do the rest of the work using this reduced function. You no longer need to look at the original one. So on to the next step, vertical asymptotes. To find the vertical asymptotes, we just need to set the denominator of the function equal to 0. And we get two solutions. We get x equals -1 and x equals 1, both of which have a multiplicity of 1. Okay. Next up is the horizontal asymptote. To find that, we compare the degree of the numerator and denominator. And we can do it, in the original function or in the reduced. To be honest, it's actually probably more convenient to look at the original function here. What degree is the numerator? Third. The denominator? Also third. And when your numerator and denominator have the same degree, the rule is that you have a horizontal asymptote whose equation is y equals the leading coefficient of the top over the leading coefficient of the bottom. So it's y equals 2 over 1, or just y equals 2. And again, that is because they had the same degree on the top and bottom. Now you could have used the reduced function, and you would have gotten the same result, right? Degree 2, leading coefficient over leading coefficient, same thing. So inconsequential. Next up is the y-intercept. And to find the y-intercept, we just set x equal to 0. So we'll use the reduced function for this, more convenient. R of 0 equals 2 times 0 times 0 minus 3 over 0 plus 1 times 0 minus 1, which comes out to 0. So the y-intercept is 0. And now we can look for our x-intercepts. To find the x-intercepts, you set the numerator equals 0. And again, we can use our reduced function. So we take the reduced function and set the numerator equal to 0. 2x times x minus 3 equals 0. This is easy because we've already factored. And we get x equals 0 and x equals 3. So that's almost everything. There's one more thing we would benefit from doing. We have a horizontal asymptote whose equation is y equals 2. And it will benefit us to see whether our function intersects that horizontal asymptote. So we'll take a moment to set the function equal to the horizontal asymptote and see whether they cross. So I'll do that work over here. I'll take my horizontal asymptote, which is just 2, 2, and set it equal to my reduced function, which is 2x times x minus 3 over x plus 1 times x minus 1. Okay. Now we can, divide both sides by 2 and cancel these. Just get 1 and 1. And then what we'll do is we'll do a couple of things. First, we'll multiply both sides by the denominator so that it moves over to this side, and we get x plus 1 times x minus 1. And on the right side, we'll distribute, so we get x squared minus 3x. Okay. Next up, we'll FOIL, so we get x squared minus 1, just the difference of squares, equals x squared minus 3x. We can cancel these x squareds. And so ultimately, well, we have negative 1 equals negative 3x. So 1 equals 3x. Or x equals 1/3. So we just found out a very useful piece of information. We found out that our function crosses the horizontal asymptote at x equals 1/3. And that's a useful thing to know. So I know in advance that my function, however it looks, is going to cross my horizontal asymptote at x equals 1/3 right here. So I can make a point there. All right. Let's put all the other stuff that we found on here. Vertical asymptotes we have at 1 and negative 1. Let's throw them on here. Vertical asymptotes at 1, x equals 1, I should say, and x equals negative 1. And then, let's see, we have a y-intercept at 0. And no surprise, we also have an x-intercept at 0. And look, I forgot to mention the multiplicities of the x-intercepts. They both were a multiplicity of 1. So yeah, our x-intercepts were x equals 0 and x equals 3. Okay, so all is situated. Okay, the next thing that we should do is graph. And let's try to use some logic here to figure out what we might expect. So the first thing is, we can pick any of these points to start out. Let's start over here on the right. And we could pick either direction. Do we want to head to the right or to the left? Well, let's see. Heading to the right, I could either go down from here or I could go up from here. But if I go down from here, I know that I ultimately need to line up with this horizontal asymptote. So I would have to go back up through the x-axis. But that would make me a new x-intercept, so I can't do that, right? So I'm going to need to go up from there. And should I cross through the horizontal asymptote? I can't. The only place I cross it, I found out, was at x equals 1/3. So there's no crossing that. So I'm really sandwiched between these two places, and I'll just approach the horizontal asymptote and head off to the right. Okay, one part done. For this x-intercept, should we go through it or should we bounce off it? Well, for two reasons. We know that we can't go back up because we can't cross this horizontal asymptote. And also, if we look at the x-intercept's multiplicity, right, x equals 3, this x-intercept right here had a multiplicity of 1. That means the graph goes through. Can we swing back up here? Nope, we'd be making new x-intercepts, which we cannot do. So we're just going to head down there. Okay. Next up, let's look at the vertical asymptote, x equals 1, and check its multiplicity. The multiplicity of this vertical asymptote at x equals 1, it has a multiplicity of 1, which means, like we talked about before, that the graph has the opposite behavior on either side. If it goes down on the right, then it's going to go up on the left. So the graph has to come down from here. Okay. And then we'll head through that point that we found from before. And we'll head towards our x-intercept. Should we bounce off it or should we go through it? Well, the x-intercept, x equals 0, had a multiplicity of 1, so we'll go through. Should we swing back up or head back down? Well, if we swing up, we'll be creating new x-intercepts, which we can't. So we'll head down here. And then, one last thing. The vertical asymptote x equals -1, its multiplicity is 1. So just like the other vertical asymptote, we have the opposite behavior on either side. On the right side, we went down. So on the left side, we'll go up. All right, so we head down from here. Should we cross our horizontal asymptote? Can't. The only place we crossed it, we already found, was at x equals 1/3. So no crossing that, and we'll just approach it, and that's it. There's our graph. So a little bit more involved in the first one, but you're really just using a little bit of logic and going through that set of steps. So hopefully seems manageable. Let's do one more. So this one, like all the others, we'll start by factoring. So the bottom, the denominator is linear with no GCF, so that's not factorable. But on the top, Let's see if we can factor this. We have 2x squared minus 3x minus 2. When I have a quadratic trinomial whose leading coefficient is more than 1, I like to use this little method. You know, some people like to guess and check, but what I do is I multiply a times c, so 2 times negative 2 is negative 4, and then I just put b, negative 3, at the bottom of this little cross, and I try to find two numbers that multiply to the top, add to the bottom. So what multiplies to negative 4 and adds to negative 3? Well, that'll be negative 4 and 1. Okay. So what I do then is I rewrite this quadratic. I leave the first and the last term alone, but I take the middle term, minus 3x, and I replace it with minus 4x plus 1x. So I'm not changing it, just rewriting it. I'll put 1x even. And then I factor by grouping. This 4-term expression that I got, it's always going to be groupable. So what's the GCF of the first group? That's 2x. What do we have left? X minus 2. GCF of the second group, I'll just pull out a 1 because there's nothing really, and I get x minus 2. What are the two factors? Well, one of them is the thing that appeared twice, x minus 2. The other is the stuff on the outside, so 2x plus 1. Okay. So that's how I like to factor problems like this. So let's rewrite f of x. On the top we have x minus 2 times 2x plus 1. And on the bottom, we just have x minus 1. All right, so we'll state the domain. This one has an easy domain. What numbers will make the denominator 0? Well, there's only one bad guy here, which is 1, right? If the denominator is 1, that's bad. Or rather, if x is 1, that's bad because 1 minus 1 is 0, but everything else is fine. So my domain will be negative infinity, comma, 1, union, 1, comma, infinity. So that's the domain. Next we look for holes. Does anything cancel? No. So no holes to be found. Next step is vertical asymptotes. To find those, we just take the denominator and set it equal to 0. We get x equals 1, which has a multiplicity of 1. Horizontal / slant asymptotes. So remember, for this, we compare the degree of the numerator and denominator. And in this special case, the numerator is degree 2, whereas the denominator is degree 1. And when your numerator is 1 degree higher than your denominator, you don't have a horizontal asymptote, you have a slant or oblique asymptote. And here's how you find it. All you need to do is divide the numerator, 2x squared minus 3x minus 2, by the denominator. And our denominator is x minus 1. So we'll do a little polynomial long division here. This is how we find our slant asymptote. Okay. So let's see. What do you have to multiply x by to get 2x squared? That's just 2x. We take that and we distribute it into this binomial. So we get 2x squared minus 2x. We'll subtract all of this. That gives us negative x. We'll pull down the minus 2. What do you have to multiply x by to get negative x? Just minus 1. And I can stop the process here. I actually don't care what remainder I get. The slant asymptote will just be y equals whatever the quotient is. I don't need to pay attention to the remainder. So we get 2x minus 1, and that's my slant asymptote. Next, I will look for any place where my function intersects my slant asymptote. And to do that, I'll just set the function equal to the slant asymptote. So this, step always takes a little bit longer than you want it to, but we'll do it. It gives us valuable information. So we'll take the slant asymptote, 2x minus 1, and set it equal to the function, x minus 2 times 2x plus 1 over x minus 1. Okay, let's do a couple of things at once here. We'll multiply both sides by the denominator, right? So that we have x minus 1 times 2x plus 1 equals x minus 2 times 2x plus 1. Oh, whoops, little mistake. This is minus. And then we'll FOIL both sides. So we get 2x squared minus x minus 2x, that's minus 3x plus 1 equals 2x squared. Let's see, that's plus x minus 4x, so minus 3x minus 2. You'll notice these cancel and these cancel, so we just get 1 equals negative 2, which, in my opinion, is not true, which means because we got no solution for this equation, remember what we were looking for. We were trying to see whether the function ever crosses the slant asymptote. To check, we set them equal, but because we got no solution, the function will never cross the slant asymptote. So let's just make a note of that. No solution, which means that the function never crosses the slant asymptote. Okay, just a couple more things for us to find, namely y-intercepts. To find the y-intercept, set x equal to 0. So we'll do f of 0 equals 2 times 0 squared. Oh, excuse me, let's use the factored version. 0 minus 2 times 2 times 0 plus 1 over 0 minus 1. What do we get? We get negative 2 times 1 over negative 1, so 2. So our y-intercept is 2, y equals 2. And to find the x-intercept, we just set the numerator equal to 0. So that's x minus 2 times 2x plus 1 equals 0. So we get x equals 2 and x equals negative 1/2. Okay, so we'll throw all this information on the graph and see what it looks like. So we have a vertical asymptote at x equals 1. We have a slant asymptote whose equation is y equals 2x minus 1. So we're just going to graph that like we would graph any line. It has a y-intercept of negative 1, right? Because this is just y equals mx plus b. So the y-intercept is negative 1. And the slope is 2. So we'll just go, up 2 over 1 to graph the next point. Up 2 over 1. Again, up 2 over 1, up 2 over 1. We can go in the other direction to get a really nice, accurate line here. Graph a bunch of points. And we'll just draw a line going through those guys. So that is our slant asymptote and how you find it. Our y-intercept was 2. So we can plot that. Y-intercept at 2. And our x-intercepts were at 2 and negative 1/2. And now let's get to work on graphing. So I think I'd like to start at this x-intercept here. And heading to the right, which way should I go, up or down? Well, I have to make it to this y-intercept, so I'll have to head up from there. I'll go through that. I can't turn around and come back down, because if I did so, I'd be crossing the slant asymptote, which I don't, and I'd be making a new x-intercept, which I don't, so I'm going to head up and approach this vertical asymptote. The vertical asymptote had a multiplicity of 1, so I do the opposite thing on both sides. If I went up on the left, I'll go down on the right. So I'll have to do this. This x-intercept had a multiplicity of 1. Oops, forgot to mention that. My x-intercepts both had a multiplicity of 1. And because they did, I'll go through it. And I need to ultimately approach this slant asymptote, so I'm just going to start hugging it as I go off to the right. one more part here. This x-intercept also had an odd multiplicity, so I go through it and approach the slant asymptote. I won't cross it because I know I never cross my slant asymptote. And at last, done. That is it for this third one. And yeah, I hope that these examples were helpful. There's a lot of steps involved in the process, but if you break it down, it's manageable. And once you practice it a few times, it gets a whole lot easier. So thank you so much for watching, and good luck. And please check out my other videos if you need, and take care.